Okay, hello, my name is Jameson Jr. and I am here to present to you my very first video regarding data science. So it's a really special video for me and I hope you like it. The purpose of this video is to walk you through all the steps that I took while wrestling with this problem. This challenge is divided into two parts, which is the data analysis of the listings of Porto and Lisbon, of the data coming from the Airbnb site. And the second part is the implementation of the decision tree to perform a classification task. So my weapon of choice is Google Colab. I chose this tool because it has zero or very little setup, and you can collaborate. Not the case for this challenge, but it is really good nonetheless because it's really organized. In here on the left, you can see all the steps that I took, and on the right, we are going to have the explanation in text, as well me speaking in the video, and the code, which you will have access. And once you see this video, it's going to be way easier to just look at the text and look at the code and just get what I mean. It's to make life easier for everyone. So here we go. We are going to dive into the data science challenge. The setup is a really quick one, just importing libraries and just installing one, because most of them are already installed. So it's really simple right there. I'm just here imputing the Lisbon CSV file that I downloaded from the site. I'm going to take the analysis for Lisbon, and then the same approach is going to go for Porto, and we are going to compare the results, okay? So here is our data. We have 16 features and almost 20K rows, so it's a good amount of data, and we can have fun with it. Next, we advance to the data analysis. So the data analysis is the part where we deal with missing values, we deal with outliers, and we see how our data is distributed in space, either space or price, and is more like really statistics based. So it's really fun, and you get to know a little bit of the behavior of our city, of my city in this case. So let's go. First, we do the initial modifications. We just drop the IDs because they just are a reference for a listing or a person, so no information there. And handling the missing values. So why do we handle the missing values? The missing values are handled because if you are going to develop a model, this model sometimes can impute the data in a way that we don't know, or they can just ignore the rows with missing data. So we don't want that. So it's a good common practice to always deal with our data so we can get the most of our resources, right? So what we do here is, firstly, we just scan the numerical values and the categorical features. We note that we have one numerical feature with 3.5K missing values. And here in the last review, the same number, so we're going to take a look into that, and some missing values in the names. What we can do here, since it's about 17% of our data missing, we are going to try to impute it. So what we're going to do is, for the categorical values of the names, we can just impute a none. So it's no problem. So it's no problem because we really don't know them. And the last review and reviews per month, they have the same value, so you can take a look to see what's going on. And we note that when the number of reviews is 0, the last review is null, and the reviews per month is also null, which makes sense because if you don't have reviews, the last review never happened, and no reviews in your month. So let's deal with them. For the reviews per month, it's really easy because you can just impute 0 if you don't have reviews, your reviews per month, no mystery there. And in the last review, it's a date value, so we have to be a little bit more careful to deal with it. What we could do if we have a different kind of data is set the first review for when the listing was created, but we don't have the information. So we can set this date into another date. I chose to be when the company was founded, which was August 2008, and count the number of days since then. So basically what we are doing here is adding another feature, and count, which is the number of days since the last review, and we are imputing data on that feature. So we have the data in a different way, which is easier to deal with, and we can deal with outliers better. Good. Now we have a classification task. Not now, but next we have a classification task, and for that we need our output. So we are going to add, we are going to discretize the feature that we are going to, our target feature, so to speak. The objective of the classification task that we are going to deal with later is the listing available for more than 280 days out of a year or not? So it's a binary. So we can look at the value of availability 365. For example, this one is 341, and we can put 1 right there because it is available for more than 280 days, and 0 else. So now we dealt with missing values, and we added some new columns. But now we are going to talk a little bit about outliers. So outliers are data that don't really fit with the rest of them, don't really follow a model. But we have to be really careful because not always data that appears to be outliers is outliers. For example, in price, we have a lot of small prices. They are really concentrated under the 100, as we are going to see. But sometimes we have houses that are thousands of euros per night because they are luxurious houses. So although it appears as an outlier, it's not really an outlier. So we have to be careful about that, and we are going to look how we are going to deal with these outliers. Let's go. With outliers here in this section, you can see that 75% of the data rests below 94 euros per night, and the number of reviews rests below 55. But here we have a listing with 20K per night. Either that's a castle or an outlier. So we are going to look into that. And we have a listing with 802. So that's a lot, because looking at these values, we can just make a little research, and I saw that the most expensive Airbnb in the world, it's worth about $12K is in the United States, and the most popular one has about 450 reviews, which is a lot. And so these values right here are obviously outliers. I actually posted all the sources here, so you can check it out, these little curiosities, because we have to look at them from an empirical point of view. Looking at outliers from a box plot perspective, not a plot, but the quartile analysis, and we want to remove these outliers. So let's take a look at what the fence values for high and low would be. And after this analysis, we can see from the calculations that a fence high for the price would be 175, which is quite low, and the low fence would be 41, so that's impossible. The host would not pay us to go there. And for the number of reviews, this number is not bad, but it's quite high, but not bad. But we cannot have number of reviews negative, so that's not going to happen. So an empirical approach was taken. Looking at the apps, the minimum value is 9 euros per night, not 0. You cannot have people there for free. I don't believe anyone would want to, anyways. And the most expensive in the world, here I have the source. It's about 12K. It's a very beautiful place. The minimum number of reviews is 0, so it's fine. and the maximum is 450, which is the value of the most popular one. So we set these fences and we remove the outliers so our data can be a little bit more clean. Next, we are going for visualization. We are going to visualize our data. So in the visualization, I took a look into the 3 most important features that I find, that I look into when I'm looking for an Airbnb, because obviously I also like to travel, and Airbnb is really convenient because it's not that expensive and you have quality places. So it would be room type, price, and location. So let's dive right into them. The visualizations here, the first, we have our room type analysis. We can see that in Lisbon, about 74% it's entire home apartments, which means that the homeowners and the listing owners really invest money into Airbnb, renting entire places for the tourists. About 22% is private room. It's either a person that divided an investment into several rooms, or a person that looks for getting money from the house that he lives, because, for example, I can live in a house with 7 rooms and it's my house, and I just need 1 room. I can rent the others and make some money out of that. So it's a smart move as well. We have about 2.1% of hotel rooms that are in Lisbon, and looking into our data and the number of data points, that's about 400 values. Okay, we have, after a little bit of research, we have about 209 hotels in Lisbon. So with 21,400 rooms in Lisbon, 400 is not a very big number. So we can see that hotels and Airbnb really are competitors and don't really work together that much. The shared room has the shared room really doesn't have a high value because the demand is not very high, because all the others values are not really that expensive, so you don't really need to share a room. Also, if you want to share a room, from a young person point of view, I would just go to a hostel, or because it's more fun and you find more people from different backgrounds there. In price analysis, I just did here KDE because it's a continuous version of a histogram. You can look at it like that. Here we have the likelihood of a listing of a certain type, and you can see that the price goes from 0 to 500. This is because for better visualization, I just chopped the plot, so we can see where the biggest values reside. And you can see, beginning here for the entire flat, which is the majority, the prices, it's most likely to find prices below 100 euros. Here about 70 or 89, 90 euros. In the private room as well, these values of the maximum likelihood, these values of the price for the maximum likelihood of each room type are very close, except here for the shared room, which is considerably cheaper than for example, the entire flats. And you can see that it has a lighter tail because you don't have that many and they're all cheap. Well, for example, entire flats or entire houses, you have from 90 euros to 900 euros, or thousands of euros in case of luxurious homes. So you have a broader price range. Okay, so we can describe our price, and 75% of the values rest below 94, which it's with accordance with our plot. The maximum value is 9,999. So I'm guessing a luxurious home there. And now we can look a bit at the mean price per region. This is a map that is divided into neighborhoods or neighborhood areas. For example, here's the center of Lisbon. Here is Ericeira, here is Cascais, and we can see the mean price value. You and me and we can note something, that here in the center of Lisbon we have lower mean value than the interior, and that's because here we are going to see later in the geospatial analysis that here you have a lot. Here you have a lot of Airbnbs, so that brings the mean price down. And this here, for example, here in Marvila, it's more for expensive houses, and the others maybe they don't have as much Airbnb listings. So that's a justification right there. It's really interesting to look at this because you can see what areas have more Airbnb or not, and where is expensive or not expensive. That serves as motivation for the next part, which is the geospatial analysis. Here we have clustered a lot of Airbnbs, a lot depending on the area, of course. For example, in the center Lisbon, we have the majority of our Airbnbs, and you can see why the mean price was so low, because look at how many Airbnbs here from this heat map and clusters, and they are just everywhere. And that's good for tourism, and it has other effects on the society. But we can see that Lisbon is a very touristic city. If you click here, you can see the price, so which is nice. Let's just take a look at another area. For example, there in which I reside, we have a lot of Airbnbs here as well, and yep, it's a good area for tourism. Luckily, that's good. Now we have the same approach for Porto. We just finished the approach for Lisbon. Now we are going to take a look how things are for Porto. I just applied the same code for Porto. So here you won't find nothing new. So 77% is entire places, 19 is private rooms, and 1.8. So it's the same kind of distribution as the city of Lisbon. For the price, we also have the price distribution. For the most of the maximum likelihoods reside below 100, and the shared rooms, really light tail here, they're really cheap, so that's in accordance with Lisbon as well. For the mean price, I don't really know the city of Porto that well, but I can guess that here is the area with more Airbnbs, and here are areas where we have less Airbnbs. So that's a motivation for our geospatial analysis. And yes, here we go. We can see the clusters and the heat map that here resides the great majority of the Airbnbs in Porto. And yeah, that's the intakes for both cities. So moving on to the classification task. For this classification task, we have here a decision tree, and a decision tree was part of the challenge presented, and I'm going to show you a little bit the motivation behind the decision tree, the intuition behind the decision tree, and then we are going to apply it with Gini, impurities, and entropy, just to compare. I'd like to stress that the objective of this decision tree is not to be great or to make nice predictions, because it doesn't, I tell you right now. But the main objective here is to show you how I would model this problem, how I would implement this decision tree, and motivate you for further research. I don't know, but it's really interesting to look at nonetheless. So here we have the intuitive explanation of the decision tree, which is the decision tree is basically a sequence of if-then questions, and these questions is used to divide our data, and the better the question, the more pure the node is. what I mean by pure is how well it divides the data into the corresponding right classes. For example, here in this case, we are going to analyze flowers, and we are going to see at the petal length, is it below 2.45? So yes, if it is, then we have our first class, Iris setosa. And this is a pure node because it classifies every sample in the same class. So it's perfect. It's clear and it's a good classification. Then we have the rest, which is not perfectly classified, and the impurity, the Gini impurity is 0.497. So you see, it's not 0.97, 0.497. Okay, so what is this split? How can we visualize the split? How can we have an intuitive notion? It's easy. 2.45 divides our data, and all our iris setosa is divided into the left part, and the rest, which is iris versicolor and virginica, to the right. So it's not pure. Now we recursively divide these unpure nodes, and we divide. It's a greedy algorithm, so it will keep dividing, okay, until the tree is, I don't know, 37 levels long or more. Too many levels lead to overfitting, but we are going to take a look at that in a moment, okay? So our fluxogram for this work is very well explained here. We have our data that we already have taken a look into. We have our training data that we are going to choose to use two ASM, which is Gini and entropy, okay? Then we are going to break the data set into subsets and then apply again, very greedy like. And then we have our testing data. We have our model evaluation, which is the performance that we all know and love, which is accuracy, precision, and recall. And let's jump right into it. So the first thing that we do is we have to divide our data into target variable and the feature vector, okay? So the feature is what we are going to use to ask the questions, and the target variable is what we want to predict, okay? And looking once again to our data, here is our training set, and we are going to divide it with scikit-learn into training and testing, okay? So using a little bit of feature engineering and selection, just a note, feature engineering and selection is that feature engineering is something that we can use to transform our data or make more features, or to transform our features and make features that will help us make better predictions. And the selection is we are going to look at the features that we have, the correlation that they have between themselves, and we are going to take out features that do not add value into our prediction. So this is what we're going to do. And to select the features that are actually good, we are going to look at the correlation of pairs. And the correlation tells us how well these features fit into a line. For example, an example of redundant features. What are redundant features? Is from one feature I can get the other, so it does not add too much value into the analysis. Reviews per month and number of reviews is clearly have one correlation because it's just a number of reviews per number of months, so it's fine. We have a correlation, a high correlation as well in neighborhood and neighborhood group, so we can get one from the other, so we don't really need. So we are going to remove some variables that do not add value. Passing on to the training and the testing, we are going to take a look at Gini and entropy. And scikit-learn really automatically trains a decision tree for us, but the result is not instantaneously the best, because We just train a decision tree using the Gini criterion, okay? And you can see that the test score is 0.55, which is not very good. And but the score for the training, that part of the data, is almost 1. So what is this? This is overfitting, a clear case of overfitting. So we can see that the tree is overfitted, and the maximum depth of the tree is 46 levels. So that's way too much. So what we have to do here is pruning. What is pruning? Pruning is what the name says. We are going to take branches off the tree that do not help achieve better results. Okay. And for that, we are going to use cost complexity pruning, which is a technique that is used for the decision trees to help take out the branches that we don't need, to regulate the depth of the tree and the number of nodes. Okay, I have here something I won't get into, which is a theoretical source. I really advise you to take a look. It's interesting as well. But sklearn, once again, provides us with an automagical answer. We just get here our CC alphas, the effective alpha values, and we are going to pass as input to the decision tree classifier all these numbers. We have 1,635 values for alpha, and we're going to pass them all. And the decision tree classifier then is going to train a classification tree with these values, which are a lot. And this is the heaviest part of the code, by the way. And it just tests for the training set, and it just fits for the training set, and then tests it and gives us a very nice perception of overfitting or not, or best results or not, which are now plotted in here. As you can see from this plot, we can see the accuracy of the training data set for this tree getting low, okay, with respect to the number of alphas, and the accuracy for the testing set, which is the objective, plotted in yellow. It's pretty constant, so the result is not going to be the best. But nevertheless, we can avoid overfitting and have a nice looking tree, okay? So the window that we can work on with alpha is from 0.0005 to 0.0024. So we are going to choose a value because the accuracy basically constant, right? And 0.0015, we have our training set score 0.55 and our test score 0.54. They're really close, so the tree is not overfitted. They are coherent, and it's not very much better than a coin toss. But once again, the objective is the methodology and the spirit behind it, not really the result for now. Here we have our prune tree. You can see that it's not a symmetrical tree, and you can see the Gini. We can see that it divides first in price, and we have here our one leaf node. This is a roof node, and these are the decision nodes. And the decisions make questions. The leaf presents Gini, number of samples, and the value, and the class that it classified. Okay, so let's take a look into a path of this tree. Okay, so first it asks, is the price lower than 21.5? If yes, it classifies it as 0, and the Gini impurity is 0.46. We have 543 right and 307 wrong. So it's not very good, but it classified it as a leaf node. And then we ask about the latitude. We have here the samples and the value. You can see that the sum of these samples give the upper sample number. And the classification, once again, for class 1, it classifies this quantity as 1 and this quantity wrongly as 1. Then we have another leaf node, and we ask another question. And then we go on with 10,000 samples. It classifies them this way, and we ask other questions until we reach all the leaf nodes are our answers. And like that, we have our decision tree. Okay. The evaluation report. The evaluation report is a very important tool that is used to see if our model is running well. The precision, we have precision, we have recall, and we have F1 score. Precision, it's how many times is the precision is quite intuitive. Is the true positive divided by the times that you got positive wrong. Okay. The recall is the true positive divided by the false negative and the true plus the true positive. So it's based on the truth, okay? And then F1 score, it's a harmonic mean between the precision and recalls. And this is an interesting measurement because it takes a look at how the model is performing overall, right? So entropy.